Today's lecture is going to be about tolerancing. Tolerancing is one of the very last steps you do on a detailed drawing. It's to define the range, the upper and lower range for every dimension on a drawing. The first step, we learned how to project your views on a drawing. Then we added dimension, but there's no such thing as an exact dimension. You can spec 1 inches, but there's no such thing as a exact 1 inch. You gotta say, all right, what's the upper limit and what's the lower limit for every dimension on a drawing. So if I were to Google search detailed drawings, that's exactly what I'm saying. For every dimension that you spec, you have to communicate an upper range and a lower range. So you can see that it can be kind of tedious, but that's what you have to do. Otherwise, you'll get all kinds of problems. Things are not going to fit right. It's gonna be a lot of rework. So you do have to spend the time to tolerance every value so that you guarantee that your product is gonna fit properly. And you see that in a lot of job descriptions. Can the engineer do GD&T, geometric dimensioning and tolerancing? Can they do stack up analysis? You hear that on meetings, you hear that on job descriptions. Sometimes just this skill set can be your job. So the first question you got to ask yourself is, what kind of fit do these two pieces have? In an assembly, you will come across a key and a keyway. A key is a symbolic term for something that fits inside a keyway. So you'll come across this thousands of times on an assembly, and you got to ask yourself, are you looking for a clearance fit or an interference fit? So a clearance fit means you guarantee that the key is going to slide in and out easily. An interference fit means that the two are going to compress. You guarantee an interference, and it's not going to slide. It's going to be like a press fit. It's going to stay there. Transition fit can be either or, but these are the two more common ones. So let's talk about the clearance fit. Like I said, the clearance fit guarantees that the product is going to slide. So, for instance, a counter bore. Counter bore is a clearance fit because you want to guarantee that the socket head cap screw is going to slide in every single time because the fastening occurs through the final threads here. Okay, so let's study the clearance fit a little bit more. Here's the key. Here's the keyway. And the darker colors here represent the range that you got to communicate. So remember, on a drawing, you got to say two things. For every dimension, you got to say, what is the upper limit? What is the lower limit? You got to figure out this value and that value, and this value and that value, because the machinist needs to know where am I acceptable. K stands for key, KW stands for keyway. So in GD&T, they have these terms called maximum material condition and least material condition. All that means is that this is the maximum material condition, and this is the least material condition. Okay, so these are just fancy terms. But at the end of the day, here's an easy equation you can use to figure out your tolerances. So it's just a plug and chug equation. Okay, a little bit of algebra. It's very straightforward. Once you get used to tolerancing, you won't even need this equation anymore. You'll just do it in your head. But you have to constantly do this math when you're designing. You're either given the key, the ranges on the key, and you have to figure out the ranges on the keyway because you have to spell that on your drawing. So you're constantly doing this equation over and over again. Okay, so here's an example. We're trying to calculate the maximum clearance and the minimum clearance given these tolerances. Here's the key, here's the keyway. So here's the upper, lower, here's upper, lower, okay? And as you can see, if you send this out to get machined, you will guarantee that the minimum clearance is going to be this and the maximum clearance is going to be that. Assuming the machinists did their job right. Assuming they did it right, your tolerances are accurate. So what I'm trying to say is not every engineer takes the time to math this out. And a lot of times the products do not come correct. Sometimes you get a dimension that's at the very, very lower limit of something that the engineer didn't predict, and you get an interference, or it gets you something you didn't want to get. And now you got to send the product back and machine it and modify it, and it's just a big waste of time. Now, just because you guarantee the clearance does mean that your product is going to be successful, because how clear is clear? If you make your clearance too loose, it can seize, because if you rotate the key by an angle, it could seize as it actuates. Or if there's not enough clearance, it clearly slides, but it may be kind of rough. You may have to hammer it down a bit. So there is a measure to how clear, and the Machinery's Handbook uses different tools, different terms, different codes to define that. And if you're not sure how much of a clearance to provide, you can check this industrial book to get an idea. The next kind of fit is the interference fit. So this is to guarantee press fit or friction fit or locating fit. So you want to guarantee that you get interference. So again, it's the same diagram, but the thing is, you want to show that these will always interfere. If it's 0, that's considered an interference fit. So just realize that if the clearance is 0, it's an interference fit. And you will notice that when you try to slide a 1-inch rod in a 1-inch hole, you need to use an arbor press to push it down. So the only difference with this is really the numbers are negative, because you want to guarantee that the clearance is negative based on the tolerances that you provide. One thing to keep in mind with interference fits is that it's very easy to overdo it. You should only aim for 1 to 1.5 thousandths of an inch of interference, especially when you're working with like stainless steel that are within 0.5 to 3 inches long or wide. Don't go more than that, because you'll get buckling, you'll get distortion, you'll get all kinds of issues. So interference fits are very delicate. It's very hard to really get the perfect value. You gotta have really tight tolerances to get the right fit. So it's not as forgiving as a clearance fit. And then finally, we have transition fits, which can either be an interference or a clearance fit. Okay, these are a little bit less common, but the idea is the same. Finally, what I want to talk about is the nomenclature. Okay. Nomenclature is how you spell the tolerances on paper. So the first way you can do that is through block tolerances, as you can see here. So when you look at a detailed drawing, as you can see, there's a lot of dimensions. You don't want to put an upper and lower limit on each of these numbers. That's going to take too much space. So instead, what you do is you put a block tolerance, and it says that if a dimension is displayed with 2 decimal places, the tolerance is going to be plus or minus 0.01 inch. If it has 3 decimal places, the tolerance is going to be 0.005 inches. So what I'm trying to say is the more decimals you place on your number, it's going to communicate a different tolerance. But if you need to deviate from these numbers, then you got to place a dedicated tolerance right next to the nominal value. One way to do that is through the symmetrical tolerance, as you can see here. Here's the nominal value, and then here's the tolerance. So I place plus or minus 0.005. So sometimes, let's say you're doing your math, you're doing your equations, and you realize the tolerance cannot be 0.01. It has to be 0.03. So when that happens, you have to bypass the block tolerance and hard type the symmetric tolerance on the dimension itself. So you can do a symmetrical tolerance, or you can do a bilateral. Bilateral means the nominal is not on the center. In the symmetrical, the nominal is on the center. In a bilateral, it's not. One end, the lower end or the upper end, is going to be different. And sometimes I've come into that situation. A lot of times I had a little bit more freedom on one side of the nominal than the other, and I decided to use a bilateral for that. A limit dimension just shows you the upper and lower limit. Some engineers like that because it saves space, so that would be a benefit. But the downside is that the operator doesn't know what your nominal value is. So a lot of times I've noticed that machinists will take the average of these two numbers and program their CNC machine for that. So you can see that there's pros and cons to using this versus this. The min-max tolerance is used to specify a range. So for example, a maximum tolerance means this value can either be 0 to 0.25. A minimum tolerance means that this value can be 0.25 or higher. The only time I've ever had to use that is for specifying reliefs. If you remember, it's very difficult to machine a sharp corner on a three-planed corner. If it's a sharp corner on three planes, it's very difficult to maintain that, and you got to machine a relief. So I usually put the max tolerance on that to communicate that I don't care if this value is less than 0.25. The only reason I'm specifying this is to make your job easier as a machinist. So I say machine this up to 0.25 max so that you can provide the relief and provide this three-plane corner. So the reason I spec up to this value is because if it's higher than that, it may cause interference problems with the other pieces that has to go in there. So you really have to figure out what is the maximum value. But that's really the only time I've ever had to use this max tolerance. I'm sure there's other applications for this, but this is the only time I personally use this. The next topic is going to be about stack-up analysis. You got to realize that when you specify a tolerance, it's going to build up. Okay, for example, in this example, you have different dimensions that are stacked on top of each other. So if you wanted to know the range, the worst case scenario range between A and B, it would be as high as 0.6 because you got to look at the stack up error of this plus that, so it'd be 0.1 plus 0.1 plus 0.1 times 2 because it goes both ways, and it's going to have buildup of as much as 0.6 inches. So that you can see how this could be a problem. Think of like an engine block that has all these parts that are connected in 3 dimensions. You can see how this could be like a stack up nightmare of parts that could fluctuate in any direction and give you all kinds of problems when you assemble it. And this becomes more of an issue when you are producing millions of these products and, going up against all the possible scenarios and Murphy's rule of the worst that can happen. You can see how this can really be an issue. But there's a way to mitigate that in the way you dimension. So if we dimension like this, where everything's stacking on top of each other, we're going to get a huge range. But if we use grouping, if you remember during the dimensioning lecture, we talked about grouping and having all the dimensions reference one reference point. When we do that, you'll notice that the range between A and B can be reduced from 0.6 to 0.4. But if you really need to reinforce the tolerance between A and B, what you gotta do is put a dedicated dimension between them. Because what happens is when you do that, these dimensions all become irrelevant. You can fluctuate this as much as you want. It is never going to affect the range that's going to happen from A to B. And when you dimension like this, your range is going to go from not only 0.6 to 0.4, but up to 0.2, because now it's just 0.1 times 2. So you can see how we've improved this tolerance by just dimensioning it differently. But the thing you got to realize is you got to understand the application. Only when you understand the application can you figure out how to dimension, put dedicated dimensions like you see here. So my rule of thumb is to first figure out your reference point, group everything to a reference point, and then if you have any critical dimensions, bypass the grouping and put a dedicated dimension where it's needed. So you may be asking, what do you mean by critical dimension? Well, for example, you may have something that slides in here, maybe a key or a keyway that slides in here, and if it's not good, if it's not the right size, if the tolerances is out, it's going to interfere and it's not going to fit properly. Finally, this slide deck just talks about a series of exercises, okay? And again, this is pretty common in the industry. You're given some tolerance and you got to figure out what to spec on the drawing for the key or the keyway. So here's an example given the key, and you can follow that equation. Just plug and chug. Follow that equation and it will get you the numbers that you need. So K is for key, KW is for keyway, and you just math it out. If you need to know the K max or the K min, you just add 0.005 to this and subtract 0.005, and you can just follow the sequence as you see here. And you can do the same thing from the other side. You're given the keyway and you got to figure out the tolerances for the key. And again, you just follow that plug and chug equation and and do a little algebra and solve what you need. Finally, the third type of exercise with this is calculating the maximum material condition and the least material condition. And really all you got to do with that is just calculate the minimum. Do 50 minus 0.1, 30 minus 0.1, and add those values together to get the minimum. and then add the maximum to each of them. And then you can see that if you were to send this out, the worst case scenarios are what you see here. This is the smallest size you will get, and this is the largest size you will get. So this is good because a lot of times you're doing an assembly with a bunch of parts and you want to know these two things. You want to know, all right, what are my worst case scenarios so that I can guarantee a successful product. And finally, on the Google Drive, I'm providing you a couple more examples of that. You're welcome to try it yourself, but again, it's asking you the same thing, find one given the other, okay? And I have 2 examples of that, the instructor exercise and the student exercise. So you can try both to get some practice with this.